Okay, hello, this is Mr. Molikash, and I'm making the first in a series of videos for Calculus BC, um, starting off with partial fractions and what partial fractions means. It's actually an algebraic procedure, and we're going to be using that to do some integrals of rational functions. So the first things we need to remember are the natural log is the integral of the rational function 1 over x. And it's important to have absolute values. Don't forget those because the natural log's domain is only positive numbers, right? Also, don't forget the plus c. And in some cases with rational functions, we'll have to do long division. I'll try to do an example of that. And in Calculus BC, it's also this partial fraction procedure that I'm going to show you is only for non-repeating linear factors. So you won't have anything other than that. Okay, so we're going to do a couple of examples here. The first thing I'm going to do is just teach you what the partial fraction procedure is. Okay, so here's a fraction, and if we had to integrate that, it would be pretty tough. We know, if this were a plus sign right here, we'd have an arctangent form, but that's unfortunately a minus. What we can do with the denominator is factor it, and that's exactly what we're going to do. So I'm going to factor the denominator into the difference of squares. So that's going to be equal to 2 over x plus 1 times x minus 1. And the goal in decomposing this into what's called partial fractions is to let each of these individual factors be singletons as denominators in their own separate fractions. And the trick, I guess, or the goal in doing this is to find out what the numerators are. And for your class, the numerators are always going to be constants. So we'll call them capital letters. We'll call this one A and this one B. And we have to use a procedure to find out what the A and B are. And again, I want to emphasize the goal in doing this is the fact that we can't integrate the expression all the way on the left. But when we get to these, we can integrate those because those are natural log forms. Okay, so the goal in doing this for calculus students is, so that we can take a more complicated integral and rewrite it into a form that's simpler, that we know the antiderivative of. Okay, all right, so before we do anything with integration, we have to figure out what these constants are. So what I'm going to do is I'm going to use algebra to try to put those partial fractions back together again. And if I do that, I can find a common denominator by taking this first fraction and multiplying it by x plus 1 over itself. Whoops, that's actually x minus 1, my fault. Because that's the other denominator, right? And then this one, we can multiply this by x plus 1 over itself. And now we have the ability to combine these fractions because they have a common denominator, right? So the put back together again fractions, if you will, on the right side, has the same denominator as the one on the left, but the numerator is going to be a times some x value minus 1 plus b times some x value plus 1. Now, to figure out what a and b are, this is really important. Pay attention to this. To figure out what a and b are, we can use convenient values for x. And what I mean by convenient values, we want either the a or the b term to disappear. And if I were to only look at it's obvious that the numerators have to be equal, right? The denominators are already equal. So we're going to make a different equation that just sets the numerators equal. So that numerator on the left side of the previous step, it's got to be equal to the numerator on the right side, right? And being that we're just looking at the numerators now, we can let x be anything we want. So I'm going to let x be -1. Now, I would not be able to put x as -1 in this line, right? Because both sides would be division by 0. But I can on this one because I'm only looking at the numerators. Okay, so when I do that, I get -2 by putting the -1 here, right? And then this one would be 0, which means that goes away, right? And so dividing both sides by -2, we know that a is -1. So we found out the constant for the first fraction, right? Okay, to figure out the constant for the next fraction, we have to play the same game, except we're going to let x be +1 in our line up here, right? Okay, so let's see if I can get rid of that. Okay, and so we're going to do 2. Now, if I put a is x equals 1 here, this is going to be 0, and then the other one's going to be 2. Of course, this disappears, right? And dividing both sides by 2 means that b is equal to 1. So now we've found our other one, right? Okay, so putting all this together, we can say that 2 over x squared minus 1 is a over x plus 1 plus b over x minus 1. And because we found out the a and the b, that makes this work. And you can check this result if you want. You can try to use Desmos calculator to graph the left and the right side, or you can try to add the fractions on the right side of this equal sign using common denominators, and it'll work out. So why do we care about this? Because if you were to have to integrate 2 over x squared minus 1 dx, you'd be like, I don't know what that is, right? But with this technique of partial fractions, we can integrate, whoops, I didn't mean to use the pencil. Okay, we can integrate the expression on the right side, and because we have 2 different fractions, we can split this up into 2 different integrals, right? So we can do -1 times the integral of this fraction plus the integral of the other fraction, and that's going to be negative natural log of the denominator of the first one plus the natural log of the denominator of the second fraction. And this is completely acceptable. You may find that you might use your properties of logarithms and have to combine. And remember that when there's subtraction, right? So remember that the natural log, or any log, of a over b is equal to the natural log of a minus the natural log of b. So because of that, we can rewrite this as the natural log of x minus 1 over x plus 1. And again, it's really important to use absolute value. So free response question, this is totally fine, but in multiple choice, you might see this form, okay? So I'm going to do another example with partial fractions just to get you kind of a little bit proficient with this technique. And then I'm going to do one where you have to use long division, and I'll explain why you have to use long division, okay? All right, so let me see over here at my textbook. I'll go grab an example. Let's see. Yeah, we'll do one with a GCF in it. How's that? So we'll just do this one here. Here's another example. So we're going to do the integral of 1 over x squared plus 2x. And right off, we've got a quadratic denominator. It's not x squared plus a constant, so we can't use the arctangent function. There's an x sitting there, right? So what we're going to try to do is we're going to use partial fractions. Whoops. I can't spell, apparently. I can only teach math. Okay. and I don't know when to use the pen or the pencil. All right. So we're going to use partial fractions to decompose this fraction into simpler fractions that we can integrate, right? So same technique as before, but what I want to do is I want to take this denominator here and rewrite it in its factored form, right? And that's going to be x times x plus 2. So that's pretty easy to see that you can, factor the GCF out of the denominator. So that means one of these denominators should be an x and the other one should be an x plus 2, right? And that implies that the numerator on the left is going to equal the numerator on the right after combining this, right? And if you get really good at this, you realize that you can multiply a times this denominator and then b times this denominator. And this works in simple fractions like this, okay? For these simpler examples, you can use that trick, right? And just like real quick, you might have learned somewhere in school that, there's something called the double cross method, so where you can do like 2 plus 3 over 6, right? And if you didn't learn that, that's okay, but you can put these together using common denominators like I did up top there. You'll take this first fraction and multiply it by x plus 2 over itself, and this next one by x over itself, and then you'll get these numerators. So just trying to save a little bit of time. That's all. All right, so we got to figure out what the a and b are. And I definitely want to use the pen. So when, let's say, x is 0, we're going to get 1 equals a times 2. So that implies that a is 1/2, right? And when x is equal to -2, and again, I hope you understand why I'm using these numbers, because I want either the a or the b term to drop out, right? Okay, so yeah, so I'm going to get 1 equals a times, b rather, my fault, times -2, which means b is -1/2. All right, so now we know what the a and the b are, and we can do this integral, right? Okay, so the integral that we were given is going to be the integral of the decomposed expression into its partial fractions. So a was 1/2, right? And then b was -1/2. Okay, convenient thing to do here is to factor the 1/2 out of the whole thing, right? And the minus sign is, I'm bringing this over from right here. Okay. All right. And yeah, so it's pretty easy to integrate now, because the first one is going to be the natural log of the absolute value of x, and then minus the natural log of the absolute value. Let me make sure that's an absolute value sign, plus c. And that's good enough for, free response. If you encounter a simplified version of this, you can have things like x over x plus 2. Remember, there's a power rule. I doubt that you ever see this expression, but just throwing this in there, remember that the natural log of a to the m, if there's a power, is m times the natural log of a. So you could have the natural log of the square root of the absolute value of x over x plus 2, because the 1/2 power, right? I doubt that you'll need to do that, but you may encounter this form on your multiple choice questions, okay? But this one is totally fine if you write this out in a free response question. Okay, so that's the nuts and bolts of partial fractions. I just want to do one more example here where you'll have to do an extra step before this, and this is something that you should have learned about in AB calculus, but I'm just going to cover it here just in case. And it's when you have to divide the polynomials, when you have to do either long division or synthetic division. And I'm gonna, let's see, I'm gonna do another example here where the numerator, this is gonna happen when the numerator, so you're always gonna have a numerator and denominator when you're integrating a rational function. If the degree of the numerator is greater than or equal to the degree of the denominator, you'll have to use division first. And you might remember for things like in pre-calculus, you might remember that when you have an expression like this means there's a horizontal asymptote, right? And you can always rewrite this as 1 plus another fraction, right? And there's a remainder, whatever the remainder is. And I think just by inspection here, I think it would be minus 1, right? Yeah, I think that's what would happen. And so then, like, you could see where if you wanted to integrate this, it would be impossible to do with U substitution. That kind of thing would be really bad. We haven't learned integration by parts that well to use integration by parts on this, and I don't think it would work on this either. So you would use this technique of doing division. And so I guess what I'll do is I'll do a couple of examples, right? So let's say that we have this integral. Okay, you should know right off that that's the arctangent, right? The integral of that expression is the arctangent. What if the numerator were x? What if the numerator were x? Well, oh, I forgot my dx up there. Sorry about that. Here you could do U substitution, or multiply that by 2 and then compensate by putting a 1/2 out there. And then this would be 1/2 times the natural log of x squared plus 1. And here I can leave out the absolute values because x squared plus 1 has to be positive regardless of what x is, right? If you put it there, it's totally fine. It's not wrong to put absolute values of positive numbers, right? So you can do that. I guess I was just showing off a little bit. All right. So those, this is an arctangent integral. This you could use U sub, right? So what happens if there's an x squared up there? Okay. Well, what you do is you do long division, and you have to do long division on this one because the quadratic denominator, right? So you would do x squared divided by x squared plus 1. And then remember, you have to put in missing terms, if you remember that from pre-calc or from math 3, right? So we'd have to put plus 0x there, plus 1. And then there's 3 terms out here, so I'd put 1 because the leading term divided by the leading term is 1, right? And then I multiply the 1 out, and that's a plus sign. Sorry about my terrible handwriting. And then what I want to do is change the signs of all these things because I'm going to subtract, right? Okay, so these drop out, and negative 1 is your remainder, right? So what I'm going to do with this integral is I'm going to rewrite it in its form where I have the quotient plus the remainder over the divisor, right? And that's going to be x minus the arctangent of x. Okay. So you may encounter having to do partial fractions when getting to this other simpler form, right? You may have to do partial fractions. In general, you can only do partial fractions when you can factor the denominator. X squared plus 1 is not factorable, The opening example, x squared minus 1 is. So, okay, let's summarize what we've learned, right? So when you're integrating a rational function, hopefully they're functions of x, okay, you'll have to remember that if the numerator's degree is 1 less than the denominator, that's going to take you to a natural log function. If they're equal degrees, like this kind of thing, then you'll have to use division first. And I want to challenge you to try that one by yourself, okay? And I'll check it in class if you want to do that. For those of you that have me in class that are watching this, yeah. And if it's bigger, then you definitely need to use division, right? Because the goal is to get the numerator to have a smaller degree than the denominator, okay? Smaller by at least 1. Now, if it's smaller by 2, then you can use the power rule, you can use substitution possibly, you can use, we have all these tools at our disposal for doing integrals, right? So, yeah, hang in there, get your work done. Definitely get plenty of practice on this. I know this class moves really fast, and AP exams around the corner for some of you. So hang in there and keep at it. Ask me questions. I'm here to help.